I told you I would show you the data for this video, or this experiment. The question was this magnetic field increases right here and then decreases, and which one would produce the greatest EMF through a coil. So if we take that, we want to look at what's the greater EMF, what's the greater change in charge, which is charge flow one way more than the other, and then what about the power? So again, we're dealing with Faraday's law. It says the EMF around a loop is the number of coils times the change in magnetic flux with respect to time. Okay, let's go ahead and answer this question. So here's the thing. If we look at the change in the EMF for part 1, we have the magnetic field increases over some area. So delta phi is constant for both of them, but delta t is smaller. And for the second one going down, delta t is longer. So that means that with a shorter time interval, EMF 1 is greater. So greater change in voltage for part 1. That was the original question. What about the current? The current is EMF over R. That's just Ohm's law. And we can also define current as the rate of change of charge. And so for current 1, that's delta Q over delta T. Now, if I solve for delta T and plug in my EMF, you can see the delta T's cancel. So the change in charge going up and coming back is the same. That's kind of cool. And what about the power? Power is IV, but if you replace V with, or I with VR, then, no, V over R, then you get V squared over R. The change in voltage is not the same. We already showed that, so the power is not the same. But what I really want to do is show you what to do. So here I have a Vernier voltmeter, I guess it's a voltmeter, and I can collect the voltage as a function of time across this coil as I move the magnet in fast and then pull it out slow. And that's what I did. And here's the data from that. You can see that right here, this is moving the magnet in. I moved it in very fast, so I get a very large voltage. Moving it out, I get a small voltage. But if you integrate the voltage over time, you get right here 0.005 volt seconds, and right here you get 0.005 seconds. So it's the same, which is kind of cool, right? Kind of cool. That's it. The end. Oh, if you want to do the power, you could multiply this by, if you want to find the current, you can multiply this by the resistance. No, you could divide, V is IR, I is V over R. Divide by the resistance, but that's just a constant, the coil. So the shape would look the same, and you get the same thing, and that's that. I'll talk to you later.